Yo, what's up, what's up? Welcome back. Today we're working on my x86 operating system. It's a Rust operating system called StreamOS, and maybe just pull up a little demo here. So what happens is I build and run my kernel, it boots in this like virtual machine, we have like this like game that started up, we can play a little break breaker, we're like drawing on the screen, we're handling keyboard input, we're handling mouse input. And on the side, let's pop up in a web browser here. While all that's happening, it's hosting like a little web server, and we can like type stuff into it, and it says like, hey, I serviced this web request on like a different CPU, and this is like, here's the data back, which proves like there's a lot of stuff going on there. There's like serial console where it's logging, it's got like a whole Ethernet stack, which means it has like PCI and address resolution and TCP and HTTP. We've got like memory allocation and like clock support, logging, unit testing, all that good stuff. And today what we wanted to work on is working towards like actually being able to run programs. So right now our operating system is really more of just a kernel, and all the kernel does is like run this like little demo, and that's kind of all it can do. And it would be nice if we could actually like run programs with it. So last stream we wrote this like world's shittiest elf loader, where elf is like the Linux executable format. So here I have this like program that runs hello world and then exits with exit code 30. And this program is pretty interesting in that there's no main and there's no like includes in it, right? This is just like a statically linked executable that's calling syscalls manually. And the reason to do that is so that we can simplify the loading process, where if I look at this program, he says like, that's not a dynamic executable, which makes the process loading much easier for us. And we also compile it with like position independent code, like relocation enabled, so that our operating system will have like the luxury of being able to like put it wherever in memory it wants, instead of having to set up like virtual memory and put the process in the right spot. Then we wrote this loader, and he basically just like reads the file, reads the loadee. He, this is all like reading stuff. He maps some memory that has read, write, and execute permissions, so that he can like copy paste the binary there and then jump to it. And then essentially all he does is just calls this like load process function, which is defined in this assembly file. And all we do is like jump to this very specific address in the process. This number 1000 was determined by like checking the headers of the program. So if I say readelf everything on loadee, we see that the entry point is at address 1000, and we carefully crafted our linker script to make sure that like the address of the offset of the data in the file itself was the same as where it should get mapped into memory. In reality, these numbers are like normally quite different, and so what you're supposed to do is you're supposed to like walk the binary, look at where each section wants to be in memory, and then put it there. And so I think what I want to do today is I want to like first upgrade our program so that it like parses the elf headers correctly and maps memory into reasonable locations. Probably not exactly what it's asked for, because it's supposed to support relocation, but at least like we won't have to like very carefully craft our linker script anymore. We also need to like parse the entry point. I want to switch over from C to Rust, because my operating system is written in Rust, and so we're going to have to eventually have some Rust code to do that. And then I want to maybe start like making a syscall interface. So right now, our loadee program, he will only work if we have Linux syscalls implemented. Like these are calling essentially Linux specific. This is Linux specific code. And what would be nice is if we could abstract that away in a way where we could then port this into our operating system and have like a call for print put somewhere that means that like our loadee process doesn't need to know details about what operating system it's running on. And if we get through all of that, then we'll probably try actually making, like, integrating the loader with our operating system and trying to run a process on there. But I suspect that we will run out of time before we get there. Yeah, so that's the plan for today. So let's say we're going to do the first thing, which is upgrade loader to Rust. I guess upgrade is probably a little bit of a misnomer. Translate loader to Rust. Yeah, okay. So I guess we'll just say cargo init. Created a binary application package. Cool. And let's just start by doing exactly what the existing program did, but in Rust. So we'll just say, look at the main, and we'll look at loader.c, and we can just essentially copy paste all of this shit and start translating. So in Rust, this is a function main that takes in nothing. This is a extern C block to tell us that there is a assembly file that we're going to be linking with. I guess maybe it makes more sense to pull this loader thing into our Rust file. So we'll see use core arch a global ASM, and we'll stick a global ASM block here that says this. So exactly what we had before. And I guess we also have to say that it's a AT&T syntax, because that's what GCC is using by default. We need to translate this function signature to be Rusty, so we can use core fpic c void. And here we need to replace this with a buff with a pointer to i8, I guess. Is that right? Yeah. And cool, so that's ready. We'll say let mute ret here instead of defining it as an int. And then we're gonna have to open the file. So here we can replace all of this stuff with Rust's version. So we can say use std fs file. I guess I want to know what we were doing there first, though. So we'll say use std fs file. And here we're gonna say file file open. Well, yeah, I guess we're gonna do it this way. File open, and we're gonna open loady like this, and we'll say if you failed to open loady. Cool. We need to find its size. So how do we do that in Rust? I already forget. Because we need to figure out how much to allocate, because we're going to be reading into like our memory mapped buffer still. We can't just do a normal file read, because we need to, if you like allocate a normal buffer, you won't be able to execute the code that's in here, but we want to execute this thing. So we need to manually call mmap from Linux, and that just means that we have to, how do I say this? We just have to like manually stick it in a mmap buffer, which means that we need to look up the size to figure out how much memory to map, essentially. So is there like a sync setlen metadata? Does the metadata tell us how large the file is? No, that's more about like if it's like a directory, symlink, etc. So probably we're gonna have to use we're gonna have to do something similar, probably where we like seek to the end and then check the size or something. Rust check file size. I assume it's the same, where it's just seek and read. Oh, metadata does have len. I missed that. All right. Let size is f.metadata expect no metadata, and we get the length. All right. And now we figure out the page size. This comes from syscall, which I guess we need to just define here. So we'll say that there is an extern function syscall who takes in probably a long, let's see, man syscall. He takes in an int, so name I32, and he returns a long. And I guess I should write I64 here instead of long, or core fic long is probably more accurate. And here we say core fic int. All right. Unclosed delimiter, so show this guy here. And sc page size, we need to look up what that was. So sc page size. How do I know what the number is? Let's look it up. SC page size number. All right, we'll look it up. So can we look? I guess this came from unitstd.h. So how do I get there? Loader, nvim loader.c. We go to. Oh, how do I know where unitstd is? Let's look at like the Nix OS definition for GCC. Presumably, it's going to throw. God, it puts so much shit in here. Is any of these things? Are any of these things include paths? Great. What a pain in my ass. What a pain. How do I find it? Run. Current system. Are any of these like includes? Software? No. God, it's so hard on like if I was on a normal Linux distro, I would just go to like user include and look. But actually like really just don't know how to get there right now. I guess I hope that if I install Clang D and then jump to definition on it, it will bring me to the right spot, I guess. Let's try that. Loader.c. And can I jump here? I can. Nice, 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 nice. So what was I looking for? SC page size, not defined in here. But I can probably just jump to this. Nice. Is define SC page size, SC page size. That's stupid. I guess we'll just print it. That's the easiest way, I guess. So we'll say printf page size num is %d, and we print sc page size, and then we return 1. gcc-o loader, loader.c, and we run the loader, and we get number 30. All right, so we'll just huck a 30 in here, and we say let here, and obviously we need this all to be an unsafe. Can I just say unsafe function main to make my life easier? Nope. I guess we'll say unsafe function main unsafe, and we'll make a function main that is just main unsafe main unsafe. Easy. Okay. Okay. So this is an assert, so we just say we replace that assert with an assert eq. Page size is equal to 4096. Just a quick little let in here. Printf is going to replace with print line. And these %ds get replaced with these guys, little curly braces. And then we need to define mmap as well. So mmap is going to be a function. It takes an adder, which is a const core fic void. Len, which is a I64 or U64, a protocol, which is a core fic int. I think that if I remember correctly, core or stood fic size t just doesn't exist for some reason. Yeah, I don't know why, so I have to put U64 here, unfortunately. Protocol flags is a core fic int. File descriptor is a core fic int, and an offset is a whatever the fucking offset t is. What do we pass in here? Ban and map off t. Maybe I have to do the same thing where to get the type, I have to look at off t and look at its definition. So we open this guy up and we look for off t and we jump to definition, and that's pretty cool. Define off t. Syscall slong type, which is slong type, long int. All right. Which makes this a I64, I guess. And what does that map return? Returns a core FFI, core FIC void, but it's a const, immutable pointer. Okay. So let's start running, like fixing all this stuff. So we'll say let buff is equal to mmap, that's fine. Core pointer null. Mmap size is right. We need to figure out what prot read, prot write, and prot exec are. So we'll just say printf prot stuff is prot read, prot write, and prot exec. Which is 7. So we'll just throw 7 in here. We need to check the map stuff, which is map anonymous and map private. Like this. So we gcc-o, we run it. So we have 34 here. And it looks like that's gonna be okay. We need to look at what map failed is, which is -1. So I guess we say 0xff, what is this, like pointer from, I guess we say not 0 as const or fic void. I think that'll do it. Mismatch types, expected raw pointer found something else. So buff is a star mute C void. Hey, is that C? We're translating something from C to Rust, so it's like half C, half Rust right now in its current state. This would be a print line. And we replace this with this. And we have no Erno, so I guess we'll just delete this for now. I don't really want to deal with Erno at this point. And something about this it doesn't like. I'm just going to come out with the rest and look at that compiler because it's bothering me. Cargo check. Types different mutability. Aha. So this should be mute. And then it works. So we seek back to the beginning. We don't have to do that because we didn't do the seek before. Then we read into this map buffer. So I guess we need to convert this into like a file read to end. And we need to like put this in our specific memory location. So read to end is maybe not what we want because this requires evacuate. We should do maybe read into this buffer. Okay, so we need to create a buffer, like a slice, a mutable slice from our pointer that we got from mmap. Oh, that's cool. I'm learning C right now. Just still in the functions team though. Just learned about Rust an hour ago. I would suggest learning C a little more thoroughly before jumping to Rust. That's just my recommendation. I think other people would have different ones, but Rust has like all these constraints that make your programs more correct, but make them a hell of a lot harder to write if you're still learning. If you're like really learning, but you know, others might have different opinions there. Okay, so let's read this file to, so we have to take this pointer and convert it into a slice. We'll say let buff slice is equal to stood slice from raw parts mute, and the data is the buffer, and the length is the page size. No, not page size, the file size. Nice. As you size. Then we just have to do f read exact. And we put the buff slice in there, I guess. Make buff slice. No method named read exact found on fs file. I thought there was. Read exact. Oh, maybe I had to include stood IO read. Okay, cool. Method, our arguments are incorrect, so he expects buff and mute u8, and this is a and mute c void. Right. Of course, right. So we need to cast this pointer to a as mute u8. Cool. And here we say mute u8 as well, and that should all work out. Types are the same. Bing bang boom. So we've read the file. We do need to do this mprotect call. I guess we actually don't need to do that anymore, probably. Because we did this mprotect call to like convert it into something that's readable and executable. But when we mmap, we should have mmapped with executable permissions already, so it should work. And then otherwise, we call load process. And load process will just convert this to take a U8. All right, so it looks like that translated. I'd be surprised if I ran this and it worked, but you know, we get surprised sometimes. You know, sometimes things work out the way we want. Let's expect here and say failed to read file. And can I run? Wow. I love it when stuff works. Okay, so what we just see here is the fact that this says hello world here, even though nowhere in our program do we type hello world, means that we've loaded our like load E process correctly. Right? Because that's what this guy's supposed to do. He says hello world via some like Linux syscalls. That's pretty sick. Okay, so we're in Rust land now. And what I wanted to do next was I wanted to like parse the elf more correctly. So we'll call, say, better elf parsing. And so I was looking at like, well, how would I do this in Rust? And I found, I just like, I did the stupid thing. I typed elf into cargo. And I'm just like, is there an elf library? And it does look like there is one that looks pretty good. Specifically, works in no STD environments, which is what we need for it to work in our operating system. Like zero allocation, and like if I look at like what this guy provides, he does seem to provide something reasonable. So I think I want to see if we can find all of the like segments that we have to load and map, as well as like where they end up, as well as the start address. And if we can get all of those things, then we can skip some of these like hard-coded, some of like hard-coded bullshit in here. So let's add to our cargo toml, a dependency on elf. Now, the usual Mick way of doing this for stream is saying, hey, dependency, that seems like we could learn how it works. And pulling in this dependency instead of like writing it myself is like a little bit atypical here. But in this case, I feel like probably parsing an elf is not very complex, right? Probably there's like a bunch of headers, and the headers are translated into stuff, and you look at those like headers and you look up the stuff from it. And since I like don't really understand what's in an elf right now, I think using this initially, even though it might have like extra complexity that we don't need, is probably like an easier way of going about this for now. Because right now I more care about like what's in there than like how it's represented on the disk, I guess. And maybe we'll even find out that if I cargo tree, this is like a 0 dependency crate. Mwah. So it doesn't even like add that much complexity for us. Love that. Okay. So let's go in here and let's see if we can, oh God, why does it look like cargo format? Much better. Okay, so the first thing that we're gonna wanna do is instead of just, I guess after we've read the buffer, we can try parsing it in some way, shape, or form. So let's pull elf bytes. And is there like a new function on this guy? How do I like make this? Minimal parse. And we minimal parse the data. So the data is going to be buff slice. And we'll say let data is this. Now he says that he needs an E. What the fuck is E? Endian parse. So I guess here we probably need somewhere we're going to tell him that we're little Indian. So here we say elf Endian little Endian. I assume, right? I'm assuming that this is supposed to remove the generics. Fuck you. Oh, it's in the wrong spot. Okay. Fine. We put it here, I think. And is that in the right spot? E should be elf bytes E. Yeah. Okay. And so maybe we can like print line. Maybe there's like a nice little debug implementation on this guy already. That would be kind of cool. Let's see. Cargo run. Look at that. Look at that. That's a nice little debug implementation. Look at all those zeros. Love that. But we see like a file header that says he's an elf64, little endian, blah blah blah. A fuck ton of zeros. I wonder what these are. This is the data. Oh, this is just the stuff in the file. That's pretty funny. This is just like a zero pattern. What a waste of space. I need that 1 kilobyte back. I can't afford that on my disk. My like terabyte long disk. Fuck that. Okay. So presumably we want to like iterate some form of headers, but what do you want to run as a test? Sorry, is that in reference to like what the hell? What are we doing right now? We have like our like load E, and we're gonna try to run this and just try to do it the same way we were doing before, but without like removing some of the hard coded stuff. Where what we were doing before was just copy pasting the binary into like a random spot in memory and jumping to it. And this is just like a low dependency way, or I should say 0 dependency way of printing and exiting. Okay, so let's see. We're gonna have, I'm assuming that like headers are important here. So if I read elf -h, I'm assuming -h means header. I'm actually just fucking guessing. I should look it up, but fuck that. And I look at the load E. That's the elf header. So he has entry point address in here as one of the many things. So I wonder if we can look at the header of our thing. So we have a file header. And one of these things is the entry point, which is in virtual memory. So we don't have virtual memory on our operating system, which is going to make this kind of weird. But I think we can assume that what it thinks virtual memory is, well, we can pretend that our virtual memory space is a one-to-one mapping of physical memory. So in that case, we do have virtual memory. It just happens to be exactly physical memory. We'll think of it that way for now. And so we can look at this guy probably, and he should tell us where to jump to. So let's look at that. So we should be able to say data.e is data a result? Yeah, it is. So we need to expect this. Say failed to parse elf. And so now we can look at the data and say like e header entry. And we can say print line. And we'll probably say some words here. Program entry point is the entry, and probably we want it to like be formatted as a hex number. And if I cargo run that guy, let's remove this dump of everything and just run them again. So here we see program entry point 0x1000, which is great. And then we also want to find all of the like segments that we have to load. So if I do read elf-a for everything, load d, like the part here that's important is like .text is like, where's our code? And I don't really understand a lot of this stuff yet, but I do understand that there's address and offset, and presumably one of these is like, I think offset is where is my code in the binary, and address is where does the code want to be in virtual memory. So if this 1000 matches with this 1000 because the start function is at the start of the entry point is the beginning of all of our code. So I want to maybe see if we can find that in here. So I'm assuming there's either segments, sections. Does it say in here what these are? This says that they're section headers. So if we look at our little API here, probably there's some iterator over sections, I would guess. Section data comes from section header by name, section headers with stir tab. I don't know what the fuck a stir tab is. String table. Okay, that makes sense. So probably somewhere there's going to be like indexes into a string table, and we need to look those up. Section headers is probably the one we want to look at. So let's do that. So we'll say for section header in data.section headers, we'll print line the header. And probably it's got a nice little debug implementation for us. And we'll look at what it has in there. Header. Cargo run. So that's kind of weird. Only one header. I kind of assumed there would be more in there, right? Because when we call read elf, we see all of these guys, right? 1 through 9. So what are we getting here if not that? Let's look at segments as well. We'll call this section, and maybe we'll do the same thing with segments. Oh, it's because it returns an option. I see. So this returns an option of section header table, which is a parsing table, which has an iter. That's more what I want. Okay, so I want this section headers unwrap or expect failed to get headers. And then I want to get the iterator of that. Yeah. Ah, much better. Okay, so the problem was that I was iterating an option, and when you iterate an option, it like, I don't know why options cast in iterators. There's probably a good reason for that. But it just means that like if there's something in there, you'll iterate over one thing, and if there's nothing in there, you iterate over 0 things. And so I was just iterating over like the outer thing when I want to iterate over the inner thing. Okay, so here we have section headers that have indexes presumably into the string table. So here, these guys say what their names are in our like read elf output. So let's assume that these sh names are something that we should be able to look at. And so probably if we iterate with string tab, we should be able to get that out. I don't know if we like, I don't know why I would call section headers with stir tab when I could pull the stir tab out separately. So I'm going to try to do that. Stir tab. Maybe because no one, like this guy doesn't just let me get the string table. He has section headers with stir tab, dynamic single table. Yeah, interesting. So there's probably some reason for that. So I'll just call this function that's Oh, section data as stirtab. This is maybe what we want. Ah, so the string table is probably one of the many sections in here. How do we tell that? If section is not of type ABI shit stirtab. There's no way SHT I'm supposed to pronounce that shit. Something I don't have a good guess. Elf ABI, I'll just call it shit stirtab, and so that's 3. So probably one of these guys has a type of 3. 2 of these guys have a type of 3, which is kind of interesting. There's 2 string tables, and their names come from themselves, maybe, or SHT type, SH flags, SH header, offset, size, link, info. Yeah, that's interesting. I wonder why there's 2. So this is the last 2 entries in here. So they have stirtab and syscall, which are both of type string table. Okay, sure, whatever. So I guess when one of these guys who says get section headers with stirtab, it looks for the corresponding string table. It like iterates this like once for you, finds the string table, and then brings it back, I guess. All right, sure, fuck it, let's do it. So here we'll say let what we have the sections and stirtab string table is equal to data section headers with stirtab. Expect failed to get headers. I started rewriting my small compiler from C++ to Rust. I hope it goes well. Is this a compiler for an existing language, or is it a compiler for a new language? Can't stand C++ anymore. C++, yeah, I think it's, you know, I had to write it a lot for work, which, you know, it's fine, but there's a lot of stuff in there where it's like, man, that didn't do what I thought it would do. Right? Like, you just, like, you call, like, remove on a vector, and it just, like, does something that you did, like, it doesn't work the way you would expect. Or, like, what is it? The stood algo remove doesn't actually remove stuff. Like, the library is just, like, full of that shit. I find that in Rust, when I guess what an API does, I guess right. And that in and of itself is, like, such a huge benefit, man. It's so tiring to, like, have your program crash and you be like, why? And you just like, oh, stood move doesn't move anything. Stood remove doesn't remove anything. It's just am I using Bevy? Isn't Bevy a game engine? I'm not writing a game right now, so no. But I've never actually looked at Bevy, so I don't. Maybe I'm missing something that would make it make sense for me to use it here. Okay. So what am I doing here? I'm trying to iterate my sections and get their names. So we're gonna say for section header in, I guess we have to unwrap each of these. So we'll say let sections is equal to sections, expect no sections, and we'll say string table is equal to string table expect no string table. And then here we're gonna iterate over sections.iter. Just joined. Okay, yeah. So what we're doing is we're working on an operating system, and what we're working on right now is like proof of concept process loading. So we're trying to figure out how, like, when we load a process on Linux, we've kind of made this like proof of concept where it replaces itself with another binary, but without going through the like Linux syscall to do that. And now we're trying to like turn that into some Rust code, and then we're going to pull our Rust code into our operating system and see if we can like use that to spawn processes from our OS. And what we're doing right now is we're trying to improve it a little bit, where we're like parsing the process table. We're processing like the metadata of the process, parsing the metadata of the process to get a better feel for like what we have to do, because we took a lot of shortcuts yesterday. Okay, so we have this section header, and it would be nice to get its name. So we'll say that the section name must have some form of way to look up in the string table what it is. So we probably have like let section name index is going to be something in here. Sh name, I'm just guessing, but that seems very likely. So we're gonna have the header sh name. And here, probably the string table is going to have some way to look something up. So we can say get here. So we say let section name is string table dot get section name index. And we'll expect when we say no name, brownie face. He doesn't like that this isn't the right thing, so we'll just say as usize. I'm not actually sure this is right, but we'll find out. And then we'll print the name. And we'll cargo run. And this looks right. So we're seeing a name of text. So like if we look at like the readelf output, we see sections that say nothing, text, RO data, EH frame header. And if we look at what we have nothing, text, RO data, EH frame header. So it looks like it's right. Which is pretty cool. So we're getting a better understanding of like what the fuck are in these things. Okay, so I've seen some like references to this thing called like pt load in elf headers, and I think that means that it's like a section that you're supposed to like basically map from the binary into your process space, I think. But I just made that up, so it would be nice to, oh my god, decline all. pt load. So these come from like segment types, and they can be load, dynamic, interp. Okay, and what do these guys mean? Loadable segment. The bytes from the file are mapped to the beginning of the memory segment. If the segment's memory size is larger than the file size, the extra bytes are defined to hold the value 0 and follow the segment's initialized area. The file size can not be larger than the memory size. Okay. PT dynamic specifies dynamic linking information. So I wonder if, so I compiled my program with position and independent code. So I wonder if that means that like it could be dynamic, if it will come up with PT dynamic. So where did this say this comes from? This is from some segment type. So I wonder if in here we have a segment type available to us. Let's see. So we have a section header table, and this guy iterates over section headers, and one of these guys should be a type, section type. Nice. And so we have this mapping of section types here, and can we like can we look at what those are and try to correlate? So here our text section is 1. 1, 1, 1, 1. Okay. And so somewhere in here we had pt load. And pt load means that we put the thing described by file size and memory size to the beginning of the memory segment. Okay, so we're just fucking cheating, by the way. We are putting a constraint on here that says, hey, your code has to be relocatable. Just to be clear, there are segments and segments in ELF. They're not the same. Oh, segment types, and I'm in section header. Oh, good catch. Thank you. Thank you. Good catch. So it's pretty weird. Why do these line up? Like, why did that work the way, like, I would have thought that I would have just got the wrong thing. So we have program header. Program header is, oh, this is the program header. I want the segment types, and I'm iterating. Am I iterating segments or sections? I'm iterating sections. So section header he has an sh type, which is the section type. So can I look up section type? Elf? So I'm seeing the number 1, which is prog bits. Is that reasonable? Maybe. Oh yeah, these are saying prog bits. So I was just associating prog bits with load, which was just wrong. Okay. Cool. And so this section holds information defined by the program whose format and meaning are determined solely by the program. This second and SHT-rel, this section holds relocation entries without explicit add-ins, such as elf32rel. Okay. So eventually we're probably gonna have to figure out how to like actually define a relocatable binary. But for now, I'm just going to ignore that. So what is a segment then? Why am I getting those things mixed up in my head? Let's print out the segments and see. So here we're just gonna say let segments is going to be data segments. We'll say fail to get segments, and we'll iterate them. So we'll say for segment in segments, I assume that there's an iter in here. Cool. And can we just print line the segment? Let's see what that says to us. So we have segments that are program headers that have these like mappings of virtual adder, physical adder, file size, memory size. Okay. So maybe we just map these program headers as they would like. What are these p-type big-ass numbers? What do those mean? Elf segment type. Elf 101. That's me. 101 might be a little too advanced. We're just guessing. We know nothing right now, so maybe we're looking for elf 001. Okay, segment tables, no. Program header, no. I want segment type. 0 equals null, ignore the entry. 1 is load. 2 dynamic. But what are like, where's the big ass number coming from? Let's print these as hex, I guess, just to see if that gives us something else. Like maybe they'll become clear. Program type is just like, fuck, like what are these? What are these? Elf segment types. Can I just like paste this? Obviously not, right? I think I saw something in like the Oracle thing I was looking at before. Oh yeah, here. They had like extra types in here that were big ass numbers, but none of these big ass numbers are matching what we see. So are these just like corrupt? Read elf low D. So this guy has segment sections 0, 1, 2, 3, 4. And we're seeing 0, 1, 2, 3, 4. Okay. But then like note, these are notes and EH frame headers. So these might be debug information. It does seem that way, but like how am I supposed to like understand these types? Note new property segment type. Outside of elf segments. That's not what I want. Okay, well I guess we'll just for now we will just only parse loads, and anything else we'll just log and write I don't know what the fuck that is. And if we crash, we'll understand that there's something wrong, and if we don't crash, we'll just assume it's right for now, even though it's almost certainly not. Oh, program headers. Maybe this is related. Load note GNU stack. GNU property. Am I supposed to say GNU? I've been saying GNU as like a joke for like my entire life, but I don't know if that's actually how you're supposed to say it. GNU pronunciation. It is pronounced with one syllable with a hard G. Group with like, oh, okay. So maybe that's why. Maybe I just think that's funny, and that's why I've been saying it as a joke my whole life. I don't know, man. Okay, so let's iterate the segments, and we'll look for loads. And we're going to assume that since we have compiled our load-e with relocation enabled, which is important because we don't support virtual memory in our operating system yet, probably what we can do is we can find the lowest address and subtract that from all of the load segments, and then when we copy paste into our like executable section, then that should be okay. So let's do that. So let's say maybe we'll say function copy load sections, and we're going to take our elf data. I think it's like elf bytes e, where e is something. E is like endian parse. And elf bytes is from elf. And we're going to iterate the segments, and we're going to find the smallest one. So we're going to say let segments is equal to data segments. And we're going to say let smallest address is segments iter min. Do they have a min by? Nice. What's the difference between min by and min by key? Min by gives us something, a comparison operator, and min by key gives us just a number that will be passed into a comparison later. So I guess we can do min by key, and we're going to say v dot segment v-adder, I think is what it's called. I don't know why that's not popping up in our thing. So let's see. Iter returns a parsing table. Segments is a option parsing table, so that's the problem again. We forgot to expect. Failed to get segments, and we want p v-adder here. And then we can map by subtracting the smallest address. So let's first just say print line smallest address is this guy. And we pass in smallest address. And let's see if that tells us anything interesting. Expect failed to find smallest address. Oh, and I guess we also have to check if these are load. So we have to first filter by segment, and we should say pt or p type is equal to 1, I think. And here we want to print the address of the smallest to 1. I guess you could also do, instead of this like min by key, you could do like a map then min, like this, which is probably closer to what we want because we actually just want to pull the address out. Cool. And let's just huck a copy load sections in here and pass in the data. Okay, cargo run. And we get the smallest address of 4096, which does match up with what we see. And so then we want to copy all of this binary data into our mmapped area. So what we're going to have to do is we're also going to want to get like the largest address so that we can figure out how much memory we have to map to run this thing. So let's actually call this, instead of copy load sections, we can say get min max mapped address. And this is going to return maybe a tuple of U64s for now. We'll figure this out later. And then I guess we actually need to be a little careful here because we only want to iterate once. So is there like a min and max? No. So we can't do this, like we can't use these like fancy iterator combinators anymore, whatever the fuck they're called. Instead, we're going to say let smallest address and let largest address. And these are both mutable. And smallest address will be U64 max. And largest address will be U64 min. And then we iterate over these guys. We say for adder in this. The smallest address is the smallest address max adder, and the largest address, oopsies, this is, sorry, smallest address is smallest address min adder, largest address is the largest address max adder. Boom. And then we can say address range is this to this. Smallest address to largest address. We can call this get min max mapped address, bang, bang, boom, run. He doesn't like that because I didn't return them, of course. So return it, and we get address range 4096 to 4096. So we've clearly fucked up here because we forgot to add the size. So here we have mem size and file size. I guess mem size is what we need to add, if I remember correctly. Where did we see this? pt load. Clear mem size points at vadder, then copy file size. So mem size is the big one. It's the big one. Okay. So here we want to say adder plus, so we actually don't want to do the mapping here anymore. We want to pull out segment here. This is going to be segment.pvadder, and this is going to be segment pvadder plus segment.p memsize. Boom. Boom, bing, bang, boom. So now we get a range of 4096 to 4256, and 256 bytes for our code section in this case actually like kind of makes sense. Can we look at this guy? How do we can we confirm that in some way? So 256 bytes, we're seeing basically here address 1000 to address 1070. So that's hex 70 is 127. Is that right? Python 3. 0x70 is 112. So that's actually like smaller. So maybe we're going all the way up to here or something. Sorry, AO. What is AO? 160. Huh. All right. Well, we're seeing that the the size that we have found is in fact smaller. Oh, here it actually says here. The offset file size here, mem size here, AO. Okay. And oh, we're probably seeing the load here 1000 plus A0. That doesn't really match up with the 256 we're seeing, right? Oh, because it's 256 minus 96 in hex. Print. So we say format this as hex, and let's see what that guy says. A0. Cool. Okay, we've got something right. What is a distro? Looks very clean. I'm I'm running on NixOS right now, but I think distro doesn't really matter, right? In terms of like what the OS looks like. This is just using KDE. Elf loader is fake. What does that mean? Okay. So now we have smallest to largest address. We're getting a 0, which is like the right memory size. So theoretically, we should be able to allocate only this amount of memory. And copy the loadable segments into that section. And then jump there instead, and hopefully everything just kind of works out. Hey, I don't know much about coding, but I have contacts that aren't a fan of obsessive rustations. They describe the vocal crowd as like Jehovah's Witness, but I'm curious and don't know much. Is it higher? I recommend just higher performance C or Java. Okay, so dude, that's so funny. I don't know if this is like a copy paste or like a meme, but that's so funny calling them like Jehovah's Witness. They're right. There's a bunch of loud people on the internet who basically think that Rust is like the second coming of Christ. Right? They love it. And for like, there's some good reason behind it, right? There's like a lot of things that Rust does that other languages don't. There's like the concurrency model is like very good, and it's like it protects you from, well, it has a bunch of systems in place that kind of force you to write code in like a very specific way that kind of fixes a bunch of bugs. Right? So you could kind of imagine like Rust way of writing code. Rust way, and then you can imagine like a bigger box that's like good way where there's like Rust will like force you to use a subset of like programming practices that will kind of like trick you into writing a program that will work well, is kind of like my experience with it, at least. And so people will like go all over the internet and they'll say like, rewrite it in Rust because it's better. And it's like, well, it's not better. Like there's lots of good ways to write applications, and there's lots of performant ways to write applications, but it's like pretty good. And so yeah, that's that's why people plug it so much. It's not higher performance than C. It can be, right? They're both like, they both compile down to like really close to what you wrote. So it really just depends. Both languages, they depend on like what you do as a developer. Gotta be a copy paste with the C hashtag in there. I put a lot of thought in this. If it was a copy paste, it wouldn't look like a URL. Oh, you mean C#? Oh, that's funny. Yeah, I mean, it just, yeah, I mean, I'm happy to answer it even if it is a copy paste, but yeah, I think it's, you know, I would hopefully put myself not in that group of people that is a vocal rewrite it in Rust group, and instead I just like the language. But I mean, I'm sure everybody on the internet thinks that they're that group of people as well, so you know, whatever. Okay, so what was I doing? I have now got this like address range that my program expects to be in, and we can like change our mmap to allocate that range. Is Rust your favorite? For me, yes. But I think I fall into like a specific type of programmer as well, right? Like there's programmers who really like, some people value getting stuff done a lot, and some people value correctness a lot, I guess, where I would say that like overvaluing correctness can really hinder your ability to get stuff done, just kind of like broadly speaking. Obviously that's not true all the time. And so I definitely fall on the side of somebody who would like rather have the language force me to be more correct than allow me to get more stuff done. And so there's a lot of people who wouldn't like that, and so that's totally fair, right? If you're trying to like bang out a prototype of something, a lot of people, like, you could write something in Python a lot faster often, but I would argue that a lot of, like, overall, if you're trying to get to the end of that project, writing it in Python will be harder for you, because you're going to have to like hit every error case one by one, where Rust will kind of like force you to handle all of the error cases unless you explicitly opt out of it. So I like Rust, but I can see it's not for everyone, right? That's totally fair. Okay, So we'll say min address is here, max address is here. These come out of the min max address. And we're going to want to mmap that specific chunk of memory. And we're going to say that the size is now max adder minus min adder rounded to the page size. So we say plus 4095 divided by 4096 times 4096, and so this should give this the mmap size rounded up to the closest interval of 4096. We create a buffer of that size, and hopefully if I just start mapping based off of the offsets here, this should give us something cool. So here, I guess, we're going to say for segment in segments iter, we're going to look for things that are loadable the same way we did here. So we're going to say filter for pt type 1. We'll have to factor this out eventually, but I'm not going to do that at this moment in time. And we're going to say, well, we're going to look at its virtual address. We're going to say let desired v adder is the segment's virtual adder. Oh my god. Why is this not working? V adder? Oh, because this is supposed to be segment. This. And we're going to say let mapped address is the desired address minus the min address. And then we're going to copy that amount out. They also complain about Rust devs writing bad docs. I think that's a problem with all programmers. I think there's just a lot of people's first experience that beginners aren't good at writing docs. Yeah, definitely. I mean, I will say that if you read any code I write, the docs are lacking as all hell. I've always felt it's fine from my perspective. Like, if the docs are shit, but the code exists and is readable, then it's like, I don't care. But a lot of people don't feel the same. Yeah, well, you know, I don't think that documentation is like a Rust people thing. In fact, I've read a lot of Rust libraries that have like fantastic docs. So I don't know. That's just like all programmers. I don't know. Do I have any programming book recommendations? So if you have been here a few times, you'll notice that I'm writing my own operating system from scratch. This is my alternative to reading a book, right? So I rarely read books on programming, and instead I just poke shit and guess how it works from there, and hopefully gain an understanding through that. So I'm not a book guy, but somebody else might have one for you. Yeah. Okay, so what I'm doing, I'm trying to map segments of memory into this mmap section. So here, and by map, in my case, I mean copy, because I'm trying to avoid any virtual memory. So for here, we're going to say that the mapped, we're going to say, we're going to copy from the original buffer. So here we actually should rename this to like output buff so that we don't have name collision. And I guess we should say output buff copy from the buffer that is our mapped elf file. And I guess we're going to chunk into this by segment.p offset. I assume this is where in the binary it is. And we're going to copy for segment p offset plus segment.p file size, right? So the file size is how many bytes in the binary on disk do we want to copy? And so I'm pretty sure that this will do a copy of the data that we want. And then here, when we load process, we should be able to jump to output buff instead of the buff that we were jumping to before. And hopefully that will all still work. If we still see hello world when we run this, we are fucking living the life, man. So he doesn't like that copy from is not doing what I think it's doing. Copy from slice. Oh, it's because this is a pointer. So this should be copy from, and instead we should take the address of this guy. So I think we should say buff as pointer. We'll see how this works out. Oh, this is buff. Buff is a pointer. So we'll say buff add the offset. And we will copy this many bytes, which is the segment.key file size. I got confused about types there. And this should be as usize. And this should be as usize. And then hopefully, I guess what we should do here is we should print the output buffer. Ah, fuck it. We'll run it, and when it crashes, which it does, obviously, we'll try to debug why. So the fact that the mapped address here is output buff add mapped adder. The fact that we didn't use that is pretty damning. Still seg faulting. Okay, so let's maybe breakpoint around here at the load process, and let's just take a look at what we've actually done, because I don't actually know, right? We're just kind of fucking guessing left, right, and center. So let's say gdb target debug custom loader, and we'll break at main rs line 94, and we'll run it, and let's just see what the hell we've done. So at output, let's say what is output buff, for example? This is a mute u8, right? Cool. And if we look at the contents of this guy, which we say by putting star output buff and at 100, let's print as hex because that will translate nicer. Are we seeing something sane? I guess, what do we even think we should see, right? We don't even know what we expect to see in here. So let's log what we're copying. So here we're going to say we are copying from this to this. We're going to format these as hex probably, because when you're working with memory, everything's in hex all the time because it gives you power of twos, which are nice to look at. And we're going to say they're coming from the desired, we're mapping from segment PV adder. I guess we should say P offset is where we're trying to map from to the mapped adder. Okay. So let's take a look at that. What does it say when we do that? We're copying from 1000 to 0. Hex 1000 to 0, which I think makes sense. And let's see how many bytes. So we'll say segment.p file size. So we're trying to copy 160 bytes from hex 1000 to 0 offset in our binary. Okay, that seems reasonable-ish. Let's then dump the memory that we copied. So let's say output buffer, and we're just going to log his data as hex again. Maybe we won't put a number sign here. And we're going to, let's just print 160 bytes of it. So we'll say output buff stood slice from raw parts. We'll take the output buff and we'll just log 160 bytes of it. Okay, so that's what we see. That's what we've copied into the thing. And now let's can we hex dump or maybe bless, which is a GUI hex editor. Let's look at the thing we're copying from and see if it lines up. So we have bless the loadee. Blessing it will also make it more likely to work, right? Sorry, it's a stupid fucking joke. So at hex 1000 from the binary, how can which one of these many things is hex 1000 here? So at hex 1000 we have 488D, No, this is where do I see my offset in here? Oh, here. Offset 1000. B8 100. So it looks like we've copied what we want to copy, right? We have this B810048, B810048. So it does look like we've like copied the right thing, and it looks like we have data going all the way to the end of it. And so then the question is, maybe we're jumping to the wrong offset when we try to load it, which we definitely are actually, now if I remember correctly. So let's look here, and we're trying to jump to, we're adding 1000 to the offset, so let's just stop doing that, and let's just jump straight to 0. Oopsies, wrong button, cargo run. Hey, okay, so we've copied into our thing, and now we've printed hello world, so we've got something that's like kind of reasonable. We're like running through the load addresses, we're copying them into like, we're remapping them into a different area, but that seems to be working. So now I think the last thing to do is we want to get the, we want to pull out the start address that it expects and jump to that spot specifically instead of wherever we were jumping to. So what we'll do there is we'll pull out the entry point. So we have that somewhere. I think we already pulled that out. Entry. Yeah, we have data e header entry point. So we'll say here data.e, we'll pass in data.e header.e entry minus the minimum address, and that should set the like correct entry point. So here we should be able to take in a second argument. So let's look at the x64 calling convention again. Because when we pass arguments in, they're going to show up in specific registers, and so we just have to look at what those are. So RDI, RSI. So the second thing is going to be an RSI. So we're going to want to... I guess we don't actually have to do this. We can just add this manually here. And we'll just say jump to this exact spot. So this can be add all of this as a usize. Okay. So hopefully now, this will still run, I think. Good. We still see a hello world, exit code 30, great. And now I think if we regenerate our load D, but without all of our like hacks in the linker script. So we wrote like a manual linker script that said put this at exactly address 1000, and that was like so that we could jump into the binary directly. If we just compile our thing normally now, so load-e, fuck this linker script, but still compile with position independent code and no standard library. If I run build.sh and cargo run, we still build, we still run hello world, but now we have like something completely different, right? We have our address range is big number to big number, scientific, and we have our copying is like doing something different as well. But we still run, and we still, and so now we have like less constraints on what we have to give to our operating system right now, our elf loader, which is pretty cool. So we'll call that done. Better elf parsing, load any fpic, no dep file. And what's the next thing we want to do here? The next thing that we want to do is we want to try taking out this like bullshit. Is it all ring 0 right now? Yeah, everything in the OS is ring 0. Right now, our like sample code that we're running right now actually isn't running in the OS, it's running in Linux, so this is all ring 3, but the operating system doesn't have like any concept of user space right now at all, or processes. So we're trying to get processes, then I'll probably try to do multitasking, and then maybe I'll do ring 3. I actually haven't decided if I think ring 3 is something that I want to do, because I don't really know if I'm ever going to use this for anything, but we'll see, we'll see. Okay, so what was I saying that I wanted to do next? I wanted to, oh yeah. Okay, so in our load-e, we have this bullshit in here, which is like our way of saying I want to write to the screen and then exit, But I don't want to link libc because that adds complexity to the elf loading, right? If I break like a normal application, like if I look at LDD loader, our like normal C application, he links to libc, and in order to link to libc, we need to actually like know how to like read the elf that says, hey, I would like load libc, and then we have to like figure out like how to map it, and then how to tell the actual process where it's mapped. All of that's like too much work for me. I'm trying to avoid that. And so what we have here is we're saying like no libc, we'll just manually call these syscalls to write. And what I want to do is I want to be like, well, if I were to do this on my real operating system, I wouldn't have this luxury of just being able to like hardcode syscalls in here, unless I make my syscall interface this way. And I don't think I really want to do that. I think that I don't like the concept of calling into the kernel via syscalls, especially if everything's in ring 0. I'm sure I'll find out that there's a good reason to do it this way. But I was here like, okay, extra context. When we look at like LDD output, which is like, hey, what like libraries do I depend on? Something that like almost every application has is this like dependency on like Linux VDSO. And it's like, what the fuck is that? And I think in here, there's man VDSO, which is a virtual elf dynamic shared object, which is actually like pretty cool. Like what this thing does is Linux on every process load constructs like a definition of a shared library that doesn't actually exist anywhere in the file system. Instead, it's like, here are some functions that you can call directly in kernel space, and just like, here, I'll present this to you as if I'm a shared object with functions that you can call. So you could like DL open on this guy and like look up symbols in this elf that they gave you. I guess I shouldn't put elf in quotes, it is an elf. And you could like do things like get the time without having to jump into kernel space, because they've just given you the function. And so I kind of like that as a concept. That's like pretty cool. And I would like to see like, well, how far could I get with something similar? Now, I've just talked about how I don't want to deal with mapping elf files right now. But what we could do is we could say, here's like a vtable that we pass in to our application. And in here, you could have a function pointer that's like, oh, fuck, what's like the C function pointer syntax? It's like so fucked. It's like, void star, and we'd call this like print, and he takes in a car star, right? And so we can say like, we'll pass this into our function, we'll set up some function pointers, and we'll give them to you, and all you have to do is you have to call these guys, so that we can make another one that's like exit, and he takes in an int. And then what we could do is we could take in as one of our arguments a like pointer to the vtable, which I would guess would be struct vtable star vtable. And then instead of doing this stuff, we could say like vtable, sorry, I think I fucked up a semicolon there. Then here we could say like vtable dot print hello world, and we could say like vtable dot exit 60 or 30. That's what I would like to see work. And then all we have to do is in our loader, pass this guy in, like construct our vtable and pass him as an argument. Then in our operating system, we could like put our print call and our exit call in here and figure that out later. That's kind of what I'm thinking. That's what I'm thinking. So does that compile? GCC-O, I guess we'll run build.sh. So no, because vtable's a pointer. Derp derp, so we'll do this. And otherwise, it looks like that works. And then in our loader, we just have to figure out like how we define this guy. So we'll copy paste the definition for now. We'll go into main and we'll say extern C struct vtable. And I actually don't know how to do function pointers in Rust. Rust C function pointer. Repr C. Well, okay, so these are functions. Get through pointer. Okay, so in C, they have iterate, which has a function pointer input. And then in Rust, they have unsafe extern C function. Nice, okay. Note non-nullable. And I think that if they want it to be nullable, you can wrap it in an option, if I remember correctly, but that's okay. We'll just do this for now. Okay. So do I have to set this guy as like no mangle or repr C? Probably repr C. I probably don't care about mangling. And this guy is going to be, print is going to be this guy. So he takes in a pointer to an I8. So we'll say what data is const I8. And exit is going to be the same, where he's going to have a function that returns nothing, but takes in a code, which is a core fpic int. We need a comma here. Struct is not supported in extern block, so here I guess we go like this. And oh, that makes sense. And then in extern C, this doesn't matter. And so I guess all we have to do is when we load the process here, we're going to have to pass the vtable as an argument here. So I guess we'll say we're going to jump to RSI instead of RDI, and then we're just going to set the vtable as the argument that we pass in. So here, load process is going to have the vtable as the first argument, which is going to be a pointer to the vtable. And then down here, all we have to do is make our vtable. So we'll say let vtable is equal to vtable. Our print function is going to be, I guess we probably have to like make these functions somewhere. So for now, maybe we say print or function print takes in data, which is a const I8. And this is a unsafe extern C function. And maybe we'll call this cprint just to see. Do you have to write a lot of unsafe code for this project? Okay, so for the operating system itself, generally yes. For like every driver, you have to do unsafe interactions with memory, right? Like if you have like a memory map device, in order to interact with it, to write a register on it, you do just have to write that memory. And the only way to do that is to get a pointer to it and use unsafe mechanisms. Is that okay? Sure. Right? Like I don't really see a problem with writing unsafe because it's like you're kind of just falling back to C, which is what you would have had to do anyway. Like if you were to do it without Rust, you would just do it in C anyways. And so it's like you're not really losing anything in my opinion. Also, I don't think that like unsafe should be this big spooky piece to be afraid of. I think that like there are a lot of benefits for Rust that come from things other than writing zero unsafe code. Right? So yeah, I've written a lot of unsafe in the OS, but it is what it is. Okay, so what are we going to do here when we print from C? Oh, you also have to do unsafe every time you do any like interop with C. It's just like guaranteed. So we're going to like parse this string. We're going to find its null terminator. So we'll say let length is, I guess we'll say let s is equal C stir core ffi C stir. I'll get it right one day from pointer data. And then we'll say print line, print, I guess. S, I probably have to like unwrap here. And we have to say like S as stir unwrap or something. I can't remember the API. We'll see. It'll tell us what's wrong. So this is not unwrap. What are my APIs on C string? C stir Rust. Let's see. So he can from pointer, and he creates a C stir, and then how do I get like a stir out of that? To string lossy into C string to stir. That's what I want. To stir unwrap. Okay. So let's just see if we set print to C print and exit to C exit. And I guess we have to make a C exit function that's just going to do nothing for it. Ah, fuck it. We'll just implement it. We'll implement it. C exit. So the code is a core fic int. You might wonder why I'm typing core everywhere, and it's like partly out of habit, and partly because eventually I expect this code to end up in my Rust operating system, which doesn't have the standard library. So I'm just kind of like defaulting to writing core when I could write std. It doesn't really matter. And here we're gonna say our thing is std process exit code, and that should do it. So now we pass this vtable in here, but we want to pass him as a pointer, so we put and this guy as const vtable. And I think that since now we just jump to RSI, which is the second argument, the first argument should still be RDI, and so the first argument that we get on the C side should still be the vtable. Maybe. Let's find out. Let's fucking go! Boom! Oh, that's so sick. Okay. So that's super, super cool. I'm really, really fucking stoked about that. Because that means that our load-e now, if you look at this guy, this is all he's doing. This is the whole program. And this actually has no dependency on Linux at all. And so this means that like the concept of passing in our vtable on initialization and just defining these functions from our operating system in Rust without doing any Linux syscalls or anything, I'm pretty sure that'll fucking work. And so then all we have to do when we port this into the operating system is take this vtable that we construct and construct it out of something else. That's pretty sick. That's pretty sick. What was this? What were you doing here? We were saying switch to vtable from syscall. Okay, so we're kind of like 1:30. I think integrating with operating system is probably going to be like half hour is kind of tight for that. And I don't like to go for more than 2 hours on this thing. So I think for now, I'm going to call that a day. Thank you for watching. If you liked what you saw, I stream most days around like 1 or 2 o'clock Pacific time. There's a GitHub linked in the Twitch page that like links to my profile, which has like the operating system we're working on as a whole is in there, as well as like the like keyboard overlay, the like little maze on the side, like just code I've written that goes in there. There's a YouTube link in the Twitch description as well, so if you miss a stream or whatever, all VODs will end up there. And there's also a Discord where I don't have like a good feel for what streamer Discords are supposed to be, but people have been saying stuff in there, talking about interesting things, and I've been starting to post when I'm gonna go live and like when VODs go up and stuff like that. It's pretty cool. So yeah, thanks for watching. If you're watching on YouTube, there's a Twitch link in the YouTube description if you want to come check it out live, talk, whatever. Thanks for watching, everyone. I'll catch you guys on the next one. Bye!